So today's class, we will do hybrid systems, and hybrid systems are systems which have dynamics which have a continuous phase as well as a discontinuous discrete mode. Some examples of hybrid systems are a bouncing ball. So there's a flight phase, that's the continuous phase. And when the ball hits the wall or floor, you have this discrete phase where the dynamics suddenly switch and then flies back off again. So that's an example of a hybrid system. Juggling is another one. Locomotion, walking, running for bipeds and single leg machines, and trotting, bounding for quadrupeds are examples of hybrid systems. And then when you manipulate an object, you're making contact and releasing contact, and that is also considered a hybrid system. So it's really a whole range of systems are hybrid. So it'll be interesting to model them and simulate them in MuJoCo. The example I'm going to consider is different ones, like a hypothetical example. Like it's typically if you want to have model a gymnast doing the horizontal bar and then falling in free air, then the model would be a pendulum swinging, and then you get rid of the support, and then the pendulum falls freely under gravity. And that would be a hybrid system because now there are two different modes. One is swinging about the upright position and then falling freely. So how do we model and control the system? So what I did was I created a new template called template_pendulum.zip. It's in the tiny.cc MuJoCo folder. Download that, unzip it in the my project folder. Then rename it to hybrid_pendulum, and then make those three changes. One is in the main file, make file, and the Unix file. And once you do that, open the shell, and navigate to the pendulum folder, and then either run Unix or run Windows and see if you are able to see a simple pendulum being simulated when you run the command. Okay, I'll do this steps and then we'll get started with the next. Okay, so here we are. It's the template. Unzip. Don't need this. Let's rename that to hybrid_pendulum. And that, make the three changes. Okay, here's the main.c file. Here we'll change this name to hybrid_pendulum. I'm just going to copy that. Okay, then let's open make file. Change this root, hybrid_pendulum. Then open Unix or the bat file, which is for Windows, and then change this name to hybrid_pendulum. And since we made all those changes, let's go to the shell. CD documents, MuJoCo, my project, CD hybrid pendulum, and then run. Okay, so that is pretty much the pendulum. And I believe it's in the upright position, so it's standing upright. Okay, so we've got that working. Now let's move on to the next part. Okay, now what we are trying to do here is we want the pendulum to swing freely and fall under gravity. And so we need to define this pendulum in a slightly different way. Instead of having a pendulum with 1 degree of freedom, which is the normal case, so theta, or in this case I've shown as Q1, we actually want to model the pendulum with 3 degrees of freedom. So the pendulum would have 3 joints. There'll be 2 slider joints. One slider joint will help it to move along the x-axis. One will help it to move along the y-axis. So it's the two sliding joints. And then there will be a pin joint or a hinge joint to make it rotate about the y-axis in this case. Okay, so what we'll do is we'll modify the pendulum.xml file to add these 3 degrees of freedom. And then I'll show you how you can make this pendulum fall swing freely, just like it would without the sliding joints by using this particular XML tag called equality. So let's modify the pendulum.xml and see how it goes. I think it's very helpful in this case to use the simulate command because we're modifying the XML files. So let's go to the bin folder and then click simulate. Okay, now let's dump the pendulum file here. This is what you see. I want to see where the joint is. So go to rendering and then make it show the joint. So you can see that there's a single joint, the rotary joint right here. Okay, so now let's start modifying this and see the corresponding change in this GUI. Okay, first thing I'll do is I want this pendulum to be vertically downward. So I've moved the rotated by 180 degrees. And if you now do reload, reload, so you see that it's basically switched. So basically the pendulum is hanging vertically down. Okay, so now let's start adding these joints. Okay, so it will be very similar to this. So I'll just copy this. And you need to give it a name. So let's say that first we want to define the joint which helps it to move in the X direction. So I'll call it, name is X. I know that the command, the type for a sliding joint is slide. Okay, let that remain as it is because that's going to put it exactly the place where I have the pin joint. And now the axis, you can see that the axis for the pin joint was in the negative y-axis. Here we want the joint to be on the x-axis. And so if all this works right, you will see another arrow picking out in the x direction. So reload, there it is. If you want to see how this works, what we can do is we can actually add gravity in the positive x direction. Okay, so this is going to make the joint slide in the x direction. So let's reload. You can see it's sliding in the x direction. So it looks right. So let's stop this. However, we just add the 0 again, and then reload. So it's back. Now let's add the joint in the z direction, and we just call that z. Slide is good. The position is okay, and I want it to slide in the z direction. Okay, so now what I would expect is, since it's not anchored to in the z direction, and gravity is 9.81, it should basically fall through the floor. Let's see if that happens. So it just falls through the floor. Okay, if you want to see how that looks, you might want to just change gravity to 0 and then reload. So now you can see that there are 3 joints indicated with 3 arrows. One of them is in the X, the first one, second one is along the Y, and third one is along the second one is along the Z, and the third one is along the Y, and that is the rotary joint. Okay, now let us try to figure out how to get this pendulum to stay in that position when we turn on gravity. So right now it falls. It falls because it's not fixed to the axis in the X and Z direction. So we want to make it like a regular pendulum where you're basically telling it to be fixed on the X and Z axis. So it doesn't really fall in the along the XZ direction, but just is able to rotate about the Y axis. So the command for that is in the XML, it's basically called equality. So right here should be equality. So equality is what we want. Here we basically have to connect 2 things. We basically want to connect the ground or the world frame to the pendulum. And so for syntax for this is we need to specify body 1, body 2. So one body is clearly the pendulum, the second body is the world, and then we need to tell it pretty much where we want it to be anchored. So that's, you can see that this is required, this is required. And I think that if you ignore body 2, it's optional. I think it by default takes it to be the world frame. And I think that's about it. You just need to define the anchor point. Now, anchor point is basically the point at which you want them to connect. In this case, it's going to be pretty much the place where the pin joint or the sliding joint is defined. So let's do just that. So the way this will go is we'll make another tag here, quality. And the quality. And now let's specify the connect. We specify which is the first body. Okay, now I don't think I've called it anything. This is this geometry, which needs a name. So let me just call it something. I guess pole. Okay, so that's the name I'm going to give that body because I need to use it. So pole is my first body. Second body is world. I think world is the default name given to the ground frame, fixed frame. And then the anchor is basically the position where I want them to be joined. Now, in this case, the anchor is actually this position. Okay, that's just how I defined it. Okay, and I think that will do it. So now remember that the pendulum went through the floor. I think that it will not go through the floor now that I reload it. There's an error. Let's see what the error is. Unknown element pole. Huh. Looks okay. What mistake did I do? Think, oh, I see. So the way this should go is, this is just a geometry. This is not a body. So I'm defining this name to the wrong place. It shouldn't be given to the geometry, but it should be given to the body, right? Because that's body 1. So I think now it should work fine. Let's reload. Okay, now you see it did not go in the floor. So you can uncomment this. I'm sorry, comment it out, and then you'll see that it actually goes in the floor. The moment you comment this and reload, it's fine. If you want to see it behave like a pendulum, what you can do is, I think, let's see if this works. I'm going to change the angle of the pendulum by a few degrees and see if it swings like a pendulum. So that should be Euler. This is in degrees, so it should work. Okay, now you can see that the z-axis, the xz actually rotated by 30 degrees, right? And that's because remember that the body is defined first, and then you have the x and z's, which means that the moment you specify the 30 degrees, everything below here will be rotated by 30 degrees because this is a local frame. That is, this angle would be part of x, z, and so it is basically not defined with respect to world. When I define this x-axis, it's defined with respect to this body. And since that body is rotated by 30 degrees, everything is rotated by 30 degrees. Okay, so that's fine. I don't want to do it this way. I can just do 0 and then reload. And then a better way to do this is to not change the orientation of the body, but to set the initial angle of the pendulum to some angle, 30 degrees. So let's do that in the C file and see it swinging like a pendulum without the whole thing rotating by whatever angle is specified. So let's kill this, simulate. Let's navigate back to my folder, my project. This would be hybrid Q pendulum, run Linux. Just check if it works. It looks good. You don't see the joint axis because I clearly said that in simulate. However, if you want to get the joint axis, I think it's kind of nice to have those joint axes shown the plot. And what you need to do is I've already done it for you. So right here, just before update scene, you need to set the joint to be on or off. And I actually figured out that command. It's basically a flag. And you can search for the documentation. You need to search for this particular item in API reference, and it tells you that you need to set it to 1 in order to show the joints. So let's do that. Oh, that's the COM, my bad. Okay, that's the COM. This is probably the joint. Okay, okay, now you can see the axis. In fact, if you want to see the world frame, then you can uncomment that out, and then it'll show you what the world frame is. So that's the one down, X, Y, Z. Okay, so it's too much cluttered, so I'm just going to comment out the COM and then comment out the frame, and now it will only show the joint. Okay, and now, as I said, I'm going to try to set the initial angle of this pendulum as 30 degrees. So it's 0.5. Everything here is in radians, remember. So we go there, and so 30 degrees is to the right. Okay, I would rather put minus 0.05 just because I'll use, that's how I show the animation. It's swinging, it's good. Okay, no issues. Okay, now I want to take some time and explain to you what exactly is going on here, because I think it's very important to understand the physics behind creating a floating-based system and constraining it to move in ways you care. Now, let's look at the equations of floating pendulum. So when I say a floating pendulum, it means that the base can move. So it has X, Z as the sliding joints and Q1 as the rotary joint. The equations for such a system would be of the form mq double dot plus F equals tau, and I've just expanded that M out. It's basically a mass matrix, which will have 3 rows, 3 columns that I've shown here. Q is the state. So the X, so in this case, we have the second derivative of Q. So X double dot, Z double dot, and Q1 double dot representing these accelerations. Then we have the Coriolis force and gravity forces, which will be a 3x1 vector. And then we would have external forces. So we'll have Fx, Fz, and tau over here, Fx in the X direction, in the Z direction, and then the tau y is the torque which you apply about the y-axis, which is pointing out of the plane of the paper. Okay. So when I say this, there is no pin joint, it's actually freely floating. Now, the moment you constrain the system, that is, you make the system stick at point O and don't allow it to move in the X and Z direction, then you need to modify the equation slightly. The only change you do is you add this term, J transpose FO. J is the Jacobian of the point O, and F0 are the external constraint forces at O. Okay, so provided you apply these forces at O, this system is not going to move. So think of something is moving at O, you're going to arrest that motion, and you can arrest it by applying a force. And this formula basically gives you what exactly the compensation should be. So when you expand this out, it look like this. Mx double dot, I talked about earlier, all the forces equals Fx, Fy, Fz, tau. These are the external torques. Now there are, as I said, 2 forces for the sliding joints and 1 for the pin joint. And then this Jacobian would be 3x3, and there'll be forces X, Y, and Z. Okay, now you really don't need a 3-dimensional 3x3 Jacobian. You can actually do with a, and this, I think in this case, 2x3 Jacobian, because really this motion is in the 2D plane, it's not in the 3 dimension. Okay, so what I'm going to do is I'm going to show you that you can actually check for these equations in MuJoCo. So I did this exercise for a pendulum where I showed how you can verify the equations of motion. I'm going to do the same thing for this system, where I'm going to pluck out M, I'm going to pluck out Q acceleration, these forces, everything on the right-hand side, and then just equate them and show them that's true. Once we get an idea that that is true, then we can do more interesting thing with those equations and those forces. So let's just proceed and do just that. Yes, instead of having, since we have 3 degrees of freedom, we'll have a 3x3 mass matrix, and I'm just going to generate that. So we define our mass matrix, and this is something which I always do, which is the way MuJoCo defines this mass matrix is a single dimensional array. So I need the dimension of the system. So in this case, the variable MuJoCo likes to use is NV, specifying the degrees of freedom associated with the velocity. And we can talk about why velocity, not position, later on. It's because in 3-dimension, quaternions adds another dimension, and you don't want to use that one because it's not needed. So it's typically the velocity dimension which is used to specify the dimension of the mass matrix. So NV times NV equals 0. Okay, now the function in MuJoCo used to get the mass matrix is called MJ underscore full M. So you pass in the model, you pass in the capital M in which you want to get stored the mass matrix, and then you give a pointer to something related to the dimensions of Qn. Okay, that's the syntax. Okay, so now let's, should we print it? Maybe we should print it. Zero, M1, M2. 0, 1, 2, 3, 4, 5, 6, 7. So if it was a bigger matrix, I would probably written a for loop, but for a small matrix, it's okay to just to print f. This will give a mess. So let me just write separate out 2 prints from each other on this. Okay, so you can see it's printing the mass matrix. Stop that. Okay, so we got M. Okay, we're trying to get M, acceleration, F, these forces, this Jacobian, and of course this. So all these things we can get from MuJoCo, and that's what I'm going to show you. Okay, next let's get maybe the acceleration. Okay, so I'm going to define it as QACC or Q dot maybe NV equals 0. So here we would get T dot 0 equals. So this is saved in. So if you go to the API reference, you should see that it is saved in this variable QACC. That would be the acceleration, the x direction. Then Z, and then Q. So 1. Okay, so that gives me mass, and it gives me Q. I may not print that. Let me now define the right-hand side. Sorry, it's still the left-hand side, the Coriolis and gravity forces. So F, F, F. And this is stored in, I believe it is called QFRC bias. So copy that. Okay, so what we have obtained so far is we got the mass matrix, we've got this term, acceleration, we've got F. So what I need to do now is take this term, multiply it with Q double dot, and then do plus of F, and that should be my left-hand side. So let me create a variable called LHS, carry out this multiplication, and then add this term, and keep that ready for the verification. So I'm going to create a variable called double LHS equals 0. What I do next is I multiply the mass times the Q double dot, right? And it might be beneficial to just let me make a variable called double M, okay, just to denote the dot product, sorry, the vector of the matrix times the dot of that. So equal to mass times Q dot. And I'm going to use a function within MuJoCo. It's called MJU mul mat vec. I first pass in what variable I would like the results to be saved in. So that's MQ dot. My matrix goes next. It's M. My vector goes next. This vector is QT dot. And then I need to give the dimensions of the matrix M. So it's 3, 3. So this will multiply M with Q double dot, give me the result over here. What I need to do now is to get the LHS. It's M Q dot plus F. Okay, so that's simple. It's just 0 equals M Q dot 0 plus F 0. Okay, so let's just do that for the first line, the second line, and the third line of the equations. Okay, so I have now computed the left-hand side. I'll do the same thing for the right-hand side. Let's see the equations for the right-hand side. So I need to get the external force. I need to get the Jacobian, and I need to get the constraint force. Now, I have not applied any external force on the system. So Fx, Fz, F tau is 0. If I had actually did apply some force, then they will be equal to the not be equal to 0. So if you like, you can ignore that, or let me just for completeness, Fx, Fy, tau, they will basically be, so let me call that double tau 3 NV equals. So if as I said, if it applied these forces, they would be stored in a variable called QFRC applied. So it will be 0, 1 and 2, 1 and 2. And remember, this is Fx, Fy, sorry, Fz, and this one is tau. Okay, but these are all 0. Okay, now next step is to find the Jacobian. Okay, this is the Jacobian of the constraint forces, Jacobian of O. The documentation actually offers how to do this. Now, you could, we did learn how to use MJ underscore Jack. That was in one of the previous lectures. XML API. MJ. So you can use MJ Jack to find that Jacobian. You need to specify MD, and it'll give you the, I think it's 3 by NV for Jack P, 3 by NV for Jack R. And then you need to specify which point. In this case, the point is O, and the body with whom we are trying to find the Jacobian is the pendulum, of course, pole. And you could do it this way, but you don't need to use this command. You can use a different command, because it's already there in the saved inside the MuJoCo, and so you may as well use a simpler command to find this. So the command which is used to find that is, or it's actually a variable, not a function. It's called, I think it's called EFCJ. EFCJ. Okay, EFCJ is the constraint Jacobian. So it has already done that MJ Jack calculation for you and kept that ready in this variable EFCJ. So you don't have to do this using that complicated function. Just use this. The size of this is NJ max cross NV. I checked what NJ max is. NJ max is set to some crazy 1000 or something. It's basically just a memory allocation for EFCJ. Okay, so you can only specify that number basically specifies how big a Jacobian you can have or how many constraints you can have in the system. So if you have too many constraints, EFCJ will not have proper memory allocation, you fail. So there is a clear limit on how many bodies you can simulate within this framework, provided NJMax is set to the default value. If you want to increase it, you can then change the NJMax to a bigger value, and probably you can do more collisions and more constraint forces. So in this case, we are trying to, we just have to go NV times. So in this case, there are 3 constraints. I think you'll have to just call it. I mean, you have to go 0 all the way to 9. So you will get the 3 by 3 Jacobian associated with that constraint. So let's access the Jacobian using this. So I'm going to do is I'm going to define a variable called JO, let's say, and its size is NV times NV, because we know it's 3 by 3. And then all I do is J0, 0 equals, so this actually I should write it as 3 cross NV, 3 for the X, Z, and theta, and V because NV because there are NV degrees of freedom. It just happens that this is NV is also 3, but 3 times NV is the right way of specifying this. So this would be EFC 0. Okay, I need to do that for all the 3 NV elements. So I think this one we might be better off just looping through. So 0 all the way to 3 times NV I plus plus J I, and then I think it'll give an error because I've not defined I. So let me define I. Okay, so that will give me J. Okay, and then last thing which is left to do is I need to evaluate the constraint forces. So that actually is also nicely available to you within documentation. It's called EFC, maybe EFCF, EFC, somewhere here. EFC, friction, EFC, no. I think this one. Yeah, this is a constraint force in constraint space. Okay, so EFC force. Oh, why is it 1? So let's define a variable called F0 because that's the name I gave in the presentation. V equals. So this is not right. It should be 3, right? There are 3 constraint forces because there are 3 things we're killing, not NV. So when we have F0, 0 equals the FC force 0, then I can just loop through 0, 1, 2. Now we've got all the variables of interest. Now what I do is I multiply these two together and then sum it with that, and I'll call all this stored in the variable called RHS. So first let's do J transpose times F, define J F, and that would be a vector. So similar to this, I need to take J times F. J is my input. So J0 is my input. F0 is the vector and 3 by 3. Now here's the thing. I need to do J transpose F. So, you need to transpose J first and then multiply with F. That's more work, but turns out that there's actually a function in MuJoCo which can help you to do the transpose times the vector. So if you do mulmat t, then it takes this J, takes its transpose. So it'll take this J, it take the transpose of J, and then multiply with F. So it's nice, convenient, and you don't have to transpose it separately. So now this one saves these 2 things. Now I need to define a new variable called RHS 3, 0, and all that RHS has is the following. It would be the taus, right? The tau is everything sitting here on the left side, plus this multiplication, which is the second piece. Let me just do it 3 times. Okay, now we're all set. Now let's do the verification. Verify. Just printf. %f. So I'm printing the LHS. Zero. LHS 0. Equation 1, equation 2, equation 3. A new line. Then let me not print this. Okay, hopefully everything is right and we should see that the equations are verified. Right. Okay, thanks. Okay, kill this. Okay, you can see that left-hand side is equal to the right-hand side. You can go a little backwards and see if it's all, yeah, it all looks good. If you don't like this, if you want to see zeros, you might be better off just putting LHS minus RHS, and then that way you just have to check 0. But yeah, this looks good. It looks like it's all there. Okay, so that really verifies the equations of motion for a floating base. Okay, so we verified the equations. I wrote down the equations of the hybrid system, right? MQ double dot plus F equals tau plus J transpose F, and I verified that. Now there are, in this case, there are 3 equations which I've shown you, but there are 6. Well, in this case, I know F, and then I could pretty much set that F and then show that it's verified. But in general, if you have a floating body, you need to compute the F yourself, because unless you have F, you cannot constrain the system the right way. So MuJoCo is doing that calculation. That is not something which is known a priori. So there are 6 unknowns if you want to do this without MuJoCo. The 6 unknowns are the 3 accelerations and the 3 unconstrained forces. In other words, you need to find the constraint forces such that O is O is fixed in the X and Z direction. It doesn't move around, and that is something which the physics engine does. So the question is, how do you compute F0? Turns out there's a way to do this, but there are actually not only 3 equations, but there are 3 more equations. There are 6 equations, and those equations comes from the constraint. The constraint is that I used X, but X is really the coordinates of the position O. So there are 2 coordinates. There's X coordinate, Z coordinate. So that's sitting in here. So my bad, I should have put maybe R here, not X, to denote the position of this point. So if you take the second derivative of that, then that derivative should be 0, because that this point is not moving, it's stationary. So when you take the derivative 2 times, you get this expression, J times Q double dot plus J dot times Q dot. And really where this comes from is, if you take the first derivative of X, so you get X dot, that's going to be the velocity of O. The velocity of O is the Jacobian of O times the Q dot. And obviously when you take the second derivative, you'll get something more complicated like this. Okay, so this is nothing but using the Jacobian, the velocity expression, and then taking the derivative of it to get this. So now we can write all the equations. This is the equation which I already verified, and this is the equation which I got here. I actually rearrange these equations. I move this from previous slide. I move this J transpose F to the left and move this F to the right, just so that I can club all the unknowns together. So now I have all the unknowns on the left side. There's Q double dot and F0. And then I wrote this equation in such a way that, again, Q double dot is an unknown and Q dot, which is the velocities, are all known. So then I can rewrite this equation in this form. Okay. And now we have 6 equations, because remember that 3 equations came from here, and 3 equations come from here. There are 3 equations because this is going to be the x, y, z position. So 3 equations for the 3 constraints. And we have 6 unknowns, 3 for q and 3 for f. Okay, and so this is a kind of a equation which you, if you read literature, you should see this equation come many times in the literature for Lec8 robots. They'll invariably write this equation. That is because they use a floating Bayes representation. Okay, so what we need to do now is, if you know everything on the right-hand side, which you typically do, right? Torques are things you apply. F is something which comes from Coriolis gravity terms. J and Q dot is known, it's velocities. J is the Jacobian, which is known, so you just have to take the derivative with respect to time. And everything on the right is known. And so if you invert this matrix, then you can solve for Q double dot and F0. So this has to happen every time step. And every time step, you will find the right constraint forces, so that those constraint forces, when applied to the system, will hold this point O fixed. That it will not let the pendulum fly in the X and Z direction. It will only let it rotate about the theta direction, but only rotation, not translation. Okay, so the question is, we can do this exercise. We could take Q double dot. We can write these equations because MuJoCo supplies this, and we can find F0. And then once we know F0, we can apply those forces on that pendulum, because remember that pendulum which we are thinking of is now free, and we want to simulate the system where it's flying freely, hinged to the wall for some time, and then at sudden trigger, it basically, you remove that hinge connection, and then it flies in there. So it's basically the hybrid nature. So what we can do is, we can find these forces F0 and apply them every time step, and that'll work. But I'm going to show you a trick. And the trick is to actually have 2 pendulums. So the pendulum 1, which we already have simulated, has equality constraints, and it gives us J0 and F0. We already showed that how to find J0, F0. I wrote the code. What I'll do now is, my hybrid system, which is the one I showed you, which I'm going to simulate, will be my pendulum 2. It will not have any equality constraints. So it's going to be the same XML code to get the equations, except that it will not have equality constraint. And then what I'll do is, I'll take the forces and Jacobian from this pendulum and apply onto the other pendulum. And so it will be like a, it's like we have mirror image of the first pendulum. It will always do exactly what pendulum 1 does, provided you start both pendulums in the same position. Okay. And then if you want to not show the this is like, it's like cheating, right? But if you don't want to show that pendulum 1, you only show pendulum 2, and I'll show you how to do that. You just change the transparency. Okay. And I'm going to pretty much copy the entire stuff on the pole, this one. Okay. I'll call it pole 2. Let me call this X2, Z2, pin 2. There are no more names, so it all looks good. And to distinguish the 2, let me just use a different color. I'm going to use, I think this will give me gray. The only other thing I need to do is, I need to ensure that it's also set the same way as the previous one. We don't actually have to do that. We can do that later on. Right now, the first one, remember, was set to the 30 degrees. Let me stop this thing from printing. I'm not interested in that. I just want to see how this looks when I simulate. Okay, there is a problem. Actually, I know what the problem is. It's to do with this. Because I introduced another pendulum, my degrees of freedom have gone from 3 to 6, because 3 for one, 3 for the other one. So I should define 6 here, and it should all have a problem. Okay. So you see, one pendulum went through the ground because it's not being pinned or held in the right way. Okay, so that works. Now you can see that the pendulums are one on top of each other. No, better way to do this is turn gravity off. You can see it. Okay, so they are on the same place, and that's just distracting. So I'm just going to move the pendulum slightly to in the forward direction. I think it should be plus something, if I'm not mistaken. So plus in the y direction. Let me move the position to 1 maybe. See what that does. Yeah, it's behind. Let me put it forward. So -1. I think this is better. Okay, let me turn gravity on. So now it will fall down if I don't do much. Okay. Okay, so we got that. And now let's do the interesting thing, which is compute the forces from the first pendulum and apply it onto the second one. Okay, so for that, all I need is this product. I need J transpose F, right? Because when I take J transpose F, I need to just apply that as a torque on the second pendulum to get it to work. Now, this is the issue behind doing it, which is the mass matrix has now changed. And I don't know if I have a slide for this. No, I don't have a slide for this. So original, let me write it down here. Original system has mass matrix, which looks like this: M0, M1, M2, M3, M4, M5, M6, M7, M8, right? That is what I wrote here, and that's how I got the mass matrix. Now, with the two pendulums, remember that the way MuJoCo treats the second pendulum as both the pendulum as one system. So what it will do is it'll actually give me a mass matrix which will look like this: M0, M1, M2, M3, M4, M5, and it will be 6 because now there are 3 degrees of freedom with the first pendulum, 3 for the second. So there'll be 6 columns, and then M6, M7, M8, M9, M10, M11. Okay, let me just keep writing that. M12, M13, M14, M15, M16, M17, and then you can just keep doing that. It'll be 3 more lines, and it'll end at M. So it's going to be, I mean, let me not think about it. Okay, so I'm not really interested in what is down. What I'm interested in is now my mass matrix is going to change. It's going to be these 3. So remember that the new mass matrix would be, it only be the first 3 rows, first 3 columns. So I only need these 9 numbers in order to define my mass matrix. So all I do is produce that. Let me define a new matrix, M1, and that would be 3 by, let me define a new variable, const int nv1 equals 3, and this would be nv1 times nv1 equals 0. So all I need to do now is save these in this new matrix. So 1, 2, 0, 1, 2. It's all good here, first 3, but next you see that there's a change. So if you go 0, 1, 2, 3, 4, 5. Now it will be M6, M7, M8. So M6, M7, M8, and then 6, 7, 8. So it's going to be M12, M13, M14. Okay, so I have to manually get these because they're not readily available. So this will be fine. Q double dot, there's no change. It's going to still, it'll have 7, instead of 3, it'll be 6 things, but I don't care about the remaining 3. So let me just keep it because this is my simulator, right? In the backend. F's will remain the same. I don't care too much about that. When I do this product now, what I need to do is I need to take the product of M1, right, which I just computed, times Q double dot. So this will be exactly the same. Okay, now tau, I really don't apply any force, but so just me ignore that. Okay, now let's come to J. Now J would be exactly the similar as M. Just like you had these 6 by 6, it will be a 6 by 6 J. Is that right? Yes, because the so why would J be 6 by 6? So J is 3 times NV, right? But NV is 3 times 6. Okay, so my bad. It won't be 6 NV times 6 by 6, but it'll be 3 times 6. 3 comes because of the constraints are in X, Y, and Z. And then the 6 comes because there are 6 degrees of freedom now, 3 from the first pendulum, 3 from the second. So J would be something like this. Just the M's replaced with J. It's easier to do this. This fashion. So that would be J. So what I need to do is I need to do identical things. I just need to get the first 3 in each of these rows. So it's essentially taking this code and then changing that M1 to, let's say, J1. Let's do it in this way. M1 to J1. So the only thing which changes here is be this J0 will become, let's make it here to the side. This will be J1, and then everything else will be the same. Okay, I believe you can still verify the equations. So if everything is right, it should still give me, it's true. Something changed. Okay, that failed when I, that might be true. Let's see. Still check. Oh my God. That's J0, I think. Okay, I'm going to try to, no, let's just do it this way. Okay. It still verifies, and one went down because I've still not applied the constraint force. Okay, since I verify it looks good, now I'm ready to apply the constraint force. Let's comment this out. So all I have to do is the following. I should take the forces and apply them on, I use QFRC apply to apply the forces. So QFRC applied. Now, before I do that, let's see this. Okay, so if you see this equation one more time, just this one, what I need to do in order to ensure that system is constrained is I just need to attach J transpose F0 on the first, second, and third rows of this equations. If I do that, that is, I put tau equals J transpose F, then I would have introduced the constraint force I need. And the system should, my prediction is, be the same as the one which I have simulated in the background. So this would be now, so remember that QFRC applied is external torques. And since there are 6 degrees of freedom in the system, the first 3 degrees of freedom corresponds to the first pendulum. And so I need to apply it on the second pendulum. And the second pendulum would have, so 0, 1, 2 is for the first, 3, 4, 5 is for the second one. So I need to do 3, 4, 5. And all I do is apply this force. And that's the force. Okay, let's try this. Okay, it's wobbling. It's not doing exactly what I wanted. And the reason I think is because I did not start at the same position. So let's just start it in the same position. So that would be, so here is the, wait, why did I put 0? That's not right. Q pose 0 is the X position. And that, no wonder it was moving. This should be 2, right? Because 0 is X, 1 is Z, and 2 is minus 0.5, which is the angle. Q pose. So that's for pendulum 1. So pendulum 2 again will have X, Z, theta. And so it'll be 3, 4, 5. So it'll be 5. That should be exactly equal to Q pose 2. Okay, now I think I'm setting it so that both the pendulums start in the same position, and now they are mirrors of each other. So now I believe it should work just fine. Oh, silly error. Yeah, that's better. Let's just do it a little bit, blow up the angle to, say, minus 1.57. That's 90 degrees. Okay, so there's no way to distinguish that. I mean, it's behaving exactly like that one, and I got the calculations done for free by MuJoCo. Now, if you want to make that disappear, you just change the transparency of the first pendulum. So let's make it 0. It's transparent. So it was opaque. So now you will only see one pendulum. And so now there's only one pendulum, and we don't know when background there's another pendulum going on doing the calculations for you. So that is basically using MuJoCo to do the calculations for you. It's obviously more work upfront here, but then once you get it right, then it's just a matter of setting it up in the right way. Okay, now we'll get to the final point, which is the final part, which I think is much, much easier. So we've done that. Now we want to program this system, which is now floating, the hybrid system, which is now it's going to swing as a pendulum, and then when it reaches some precise angle, it's just going to fly in the air. Okay, and so what I'll do is I'll use a finite state machine to do that. I'll define 2 states. One state is the swinging state, one is the free state, and then we'll just have fun doing the simulation. So let's do this final part. Okay, so I like to start from the very first, define my state machine. Let me not initialize it here. Let me define 2 states. FSM swing, we call that 0. Define FSM free, we call that 1. And I need to initialize the FSM. Let's go to init controller. And then our FSM here is set to FSM swing. Then we go to my controller. These calculations can remain. Okay, it's only this calculation we want to manipulate. So when it's swinging, we want to apply this calculation. When it is free, we want to just put zeros all over the place, right? So the way I like to define the FSM is this way. So all transitions first. So if FSM equal to FSM swing, then do something. Oh, sorry. If FSM swing is, if FSM is an FSM swing and some other condition is met, okay, then it needs to transition, right? And I think I'm going to just use the fact that if Q pose 2, which is the angle of the first pendulum, or even you can put the, if you want the first, instead of first, you can do the second pendulum, which is 5, is greater than, I don't know, let's say, so remember it's going from minus 0.5 to 0 to plus something. So let's say it's greater than 0, it's the vertically the downward position. Then you want to transition to FSM equals FSM free. Okay, that's just the transitions. Let's define the actions. If FSM equals FSM swing, then it needs to do this. If FSM equals FSM free, all you need to do is just clear up these forces. Okay, so let's run this. It fell. We can actually show the other pendulum. I think it'll be much illustrative if we show the other pendulum. So let's get that pendulum back to life. And then see. Yeah, that one fell because it passed 0. You can do something more fancier, like, for example, I don't know, you could do velocity control, I guess, so that it swings a little bit much faster. So let's just do that. So remember that what you're doing here is you need to apply. If you're doing anything with the second pendulum, you have to do that with the first pendulum first, so that it gives you the right constraint forces. And once it gives the constraint forces, you can apply it on the second pendulum. So here's what you need to do. So if you want to apply a velocity control so that it swings a little faster, like somebody on the bar would do. So I need to torque the system. So that's the second in the forces. So minus point. I just put minus some gain, say 1 times d q val 2, and then I want to swing it to, I don't know, minus let's say 2. So it's trying to swing it to 2 radians per second. Okay. So this is going to apply the right force on the simulated pendulum. What I need to do is take this force and apply it here. Yeah, this works. So now I can go back. This is set to, let's say, 3. Then let's go and change that to the angle, the transition condition. Let's change it to 1 point. That's too much. Let's say 1. Yeah, let me go a little faster. 5. We can actually make it look slightly better. What I'm going to do is go here to enable the contact. So that way that will fall, not go and penetrate the ground. That's one thing. The other change I would make is this plane is small. I'll increase it to 5. and you can't see it. So let's move the view down. So if you go to this will do it. This is zooming it out. 7 maybe. Yeah. Okay. Yeah. So you can play with this now. You can change that angle. That is the way to simulate hybrid systems. The commands we learned today were equality in XML, and then to find the Jacobian of constraints, EFCJ, and then constraint force, EFC force. Okay, I'll